And everyone in the workshop looked out, and I sort of looked back, and we just shrugged our shoulders and kept working. Now, it sounds funny, but it just shows how strong these machines are and the kind of quality steel that's involved in these robots. I heard a figure that there's approximately $1 million worth of manufacturing just in each grapple, including the steel. Yeah, and a few more shots of the grapple. You can see the scaffolding around the area. We sort of faked a building site where they're going to operate. I'll show you a bit more of that in a minute. Just to test our collision systems. As we can see, we're quite rigorous. And this was a video which I was going to show, but I can't show you that. We had quite a few problems with the grapple swinging around because it was just held on with a chain. So can you imagine the complexities of trying to control 1 tonne swinging at the end of a 17-metre arm with software, and it bangs around and crashes, and then the guys that build it come back and blame the software guys because our system can't control that. So we ended up replacing that chain with a much more rigid sort of link with rubber stoppers, and it made a much better action for when it was working. But this is a very rough diagram which I drew up last night, and I'll show you these guys. Oh, back we go. On an iPad, the laser pointer's not working. Well, in the middle you can see the grapples. Now they're very close together, and as you can see, they can actually swing and hit each other very easily. And they're mounted off the bottom of the pit on concrete pylons, which is 4 metres high. So we've got a 17-metre grapple on top of a 4-metre pylon in a building which is only 12 metres high. At the top of the screen you see the squares. They're actually entry points for garbage trucks to come in, open their bay doors and dump trash into the pit where the grapples sort it out. So at any time we've got one of these doors opening and trucks backing in, backing up, and the grapple actually has to know not to hit the truck because it will destroy the back of the truck and possibly kill the driver. The concrete walls all around, so they've got to dodge those walls, and basically the workflow is that they pick out items from the trash that can be recycled, such as tyres, rolls of carpet, the sort of thing that actually can't be recycled gets sorted into a different hopper, and other items get sorted into another hopper, which is that rectangle down the bottom. So the grapple has to pick the rubbish up, swing around and drop it into the hopper at that back. And the square in the centre, just at the bottom, is actually the control room. And we always thought that the control room would be out of reach of the grapples because they're at eye level. So you can imagine a claw like that coming through the wall wouldn't be very conducive to a good work day. So, oh, hang on, what's going on here? Anyway, at deployment, which just happened the last month in England, they've made the control room a lot lower than we planned. And so it's actually now possible for those grapples to hit the control room. It's fortunate that we wrote this system in Python because we were able to go in and just add a few more obstacles, and now the grapples will actually slow down before they careen through the wall. Right, this is a little gimme kaput, just to give you an idea of how big they are. I think if Optimus had to take on both of those guys at once, he'd have a little bit of trouble. So, it sounds like a great project, right? But something went wrong. About 6 months in, which is half of our project duration, we didn't have any code. We didn't have any hardware. We actually didn't have the robots either. And to give you an idea of where I sat in this project, I was just hired to write the GUI, and I was using Pygame for that, which was going to interface with the grapple control systems in whichever way we could work out. As you can see, there wasn't a lot of planning, and I won't go into details, but everyone got sacked except for the GUI guy. So here I am, faced with a project which I had no idea how to complete. And being a Python guy, I said, well, let's try and use Python. So I reached out to the community, and some of you might know of Peter Hansen. He's a real-time engineer. And I said, I want to use Python for this real-time project controlling 15 tons of steel, and it could kill people and destroy things. What do you think? And he said, don't use Python. But he said, if you really have to, don't let anyone write any code that looks like this. If big red button, emergency stop. Now, it's quite a lot of wisdom in that one line of code, and it guided the rest of the development process, because we made Python basically a control system, but we didn't make it the safety system. And I'll explain a bit more how we designed that. But that's how we managed to use Python. We ended up assembling a good team. It wasn't just me all the way through. About 4 weeks after everyone got sacked, we brought on a few more people, but not enough. So why did I choose Python? Well, you're probably all familiar with why Python's so awesome. But there's obviously a few pitfalls to using Python. It's not any kind of hard real-time. Now, to give you an idea of what hard real-time is, if an operation doesn't succeed in a certain time frame, it's considered a failure. So for things like laser cutters, they need high accuracy or medical equipment. People can die if hard real-time systems fail. And there's another problem, that Python's not really any kind of real-time because it's incredibly slow for these sorts of applications, especially on the hardware which we were using, which was gigahertz processors with limited RAM. So the question is, why did I decide to use Python considering these caveats? It allowed us to build a system very quickly. It took about 6 weeks before we had a working prototype which was interfaced with a .NET simulation. So that's 6 weeks to develop a control system. In the previous 6 months, the 3 coders that were working there before were not able to achieve that at all. And of course, it's very easy to interface with low-level C using tools like C-types or Cython or Pyrex. We ended up using C-types to interface with very low-level libraries in C, which are required to communicate with the kind of hardware we're using, which I'll describe a little bit later. Yeah, so real-time. What is real-time? Has anyone done any real-time programming before? Uh-oh. So this is probably your definition. In a hard real-time system, the completion of an operation after its deadline is considered useless. Ultimately, this may cause a critical failure of the complete system. So if our robots fail to stop in time, they could kill people, they could smash a cabin, destroy the plant, or destroy each other. So to get a hard real-time system, I decided to invent my own definition. Things had to happen within a known time frame. That was our goal, that if we asked for something to happen, if we could allow enough time for it to happen, it was good enough. If not, like a hard real-time system, it would fail. Now here's the key difference. We had to design the system so that the failure was not catastrophic. So if the machine failed to stop, it's still going to crash into something, right? So what we did is we designed a system. There it is. Wow. There's actually about 4 potential threads in that system, or 4 separate processors. And we had the control system in the middle in the green, which sort of kept all the joints in a line and set where we wanted them to be using the solenoids on the machine. And at the on the left side, we've got a system where it reads in the angles that we require the grapple to be set at, and sets the I/O blocks which control the solenoids. and I'm confused just looking at this. It was awful. And then we had the second layer on top of it, which was the joystick control system. Now, of course, I designed all this on paper beforehand, and it was just a mistake. The trick was just to jump in and write some code. So we started with the joysticks. We could read a joystick value. And then we decided, well, let's write a solenoid value. Okay, so we can control this thing. Now, what do we put in between? And we came up with a much simpler system where we've got the joysticks being read by Python, which sends some control commands out to some modules written in C, which control the I/O blocks, which actually end up controlling the grapples. And on top of this, we've got a watchdog program written in Linux. It ran in Linux using the Xenomite real-time extensions. And I'll show you how that fits in a minute. And if you look in the between the GUI and Python, we're actually using XML RPC. Now that probably makes all you hard real-time guys weep, because it's bloated and slow. But the trick was to make sure that it wasn't going to affect the running of the C routines, which were controlled by Python. Yeah, so there's a short summary. Basically, how these things work is the joysticks actually output a voltage. You don't get a nice XY tuple or data structure. You actually get a voltage ranging from -15 to +15 volts, which the I/O block will then read and convert into a digital value. And as you can imagine, there's crazy amounts of noise available in the atmosphere just to infect these signals and give you all sorts of crazy readings. And we had some real problems with these sensors, because they would say the machine was moving and it wasn't, and they'd say it was stopped and it was obviously moving. And as a Python guy reading this kind of data, and you just can't understand why computers and this equipment just doesn't work properly in the way it says it should. But apparently it's a common thing, and it was a good thing we hired the digital sound signal processing guy, because he was able to actually stream out that signal very cleanly using some Python code. And we ended up having a very accurate signal, and we could make those robots actually pick up things within, I believe it was 30 millimeters. So it's quite a feat when you consider there's a 17-meter arm on it. Unfortunately, yeah, all the analog to digital stuff is handled by these I/O blocks, which are just great little tools, especially if you're a hobbyist. You can do anything with them. So the parts which were written with Python, of course the GUI was written in Python. I wrote my own widget toolkit to work with the touchscreen, and that gave them a readout of different sensors on the grapples and where it was positioned, and why it was perhaps not moving where you thought it would be. Of course, the transport was the XML RPC. Now, I'm not an advocate of using XML RPC for anything, but it was there and it worked, and it let us deliver the project. So it's a big argument for having that sort of stuff in the standard library. Believe it or not, the collision code was actually written in Python as well, using our own custom algorithms, because we had a very specific situation we had to solve. And the fly-by-wire code, which was probably the most the fun sort of code to write, because you do things like translate a joystick pull movement into multiple solenoid movements to actually make the grapple do something quite fancy, such as when it lifts up, it might lower the boom so it doesn't go through the roof, and so you could avoid the roof in your collision code. These sorts of, it sounds like a hack, but trust me, it's like crazy what these engineers do, and you've got to really respond to these changing circumstances with whatever you can. And of course, the bottom, the automation code. Now, what was the automation? Well, that was why we can call these things robots, because they were controlled by a joystick, which could control them and place them anywhere in the pit. But it was a very tedious, boring job. So we actually had to automate these robots. A touch of a button, they could, from wherever they were in the pit, retract, swing around as fast as possible, and dump their rubbish in the pit. Sorry. And of course, then it had to go back to where it was originally located. So there's some path planning, some collision avoidance, and that sort of thing, all written in Python. It was basically just a big script which allowed these machines to spin very quickly, so they could actually move faster than the operators could move them with the joystick while they're in the automated mode. And that's ultimately why we could call them robots. Now the parts we had to put in C, we put some vector libraries and some geometry stuff in C, mainly because it's the guy that was doing it, his preferred language, not really because of any speed requirement. And the watchdog timer, which watched the whole system to make sure that failure was not catastrophic. And the low-level I/O protocols were written in C libraries too. So how can I claim that this was hard real-time? Well, the Python components we knew would get there in the end. Ultimately, Python will do its job. But if for some strange unforeseeable reason it didn't, the ZenMI watchdog would drop the network. Now that seems a bit crazy, right? Why would you drop the network from your control system to your equipment? Now this is the hard real-time bit. The I/O blocks were designed so that if the network dropped, they would respond within 30 milliseconds and halt the machines. So they would set all the solenoids to stop, and the machines would stop as quickly as they could. Now you can imagine if these machines are spinning at 72 kilometres an hour, a sudden stop is probably going to tear them apart. So we had to put another piece of equipment in there, which was like a hydraulic brake. And basically, machines would spin and put so much pressure on this brake that it would give way, and the machine wouldn't spin continually, but it would slow down very rapidly. And while we were testing this, the machines were about 30 metres away from us. When this brake came on, the ground shook. It was a staggering amount of power just coming out of these machines. Right, so I'll just plug in a video. As the project came to its conclusion, we realised we had just a few hours left to do with these machines something that we'd never forget, because they were being dismantled the next day. So what we did, unlock it. We went down to Harvey Norman and bought a Wiimote. We got some nice, cheap open source libraries from Google Code to interface with the Wiimote from Python. And we essentially replaced the joysticks with the tilt sensors which are in the Wiimote. And this was the video. I'll just plug in the audio. There's a bit of audio too.
Hello, my name's Simon. It is Bender and Fender, our 15-tonne grapples. That's 15 tonnes each.
Right.
Start that again. Ads and everything, eh?
Oh, it's a bit rich.
Hello, my name's Simon, and this is Bender and Fender, our 15-tonne grapples. That's 15 tonnes each. Each grapple has a reach of about 16 metres and needs to operate in a confined space. It needs to avoid collisions with the other grapple and with other obstacles inside the building. At full speed, the grapple can spin around at about 72 kilometres an hour, which is roughly 12 revolutions per minute.
So you can imagine how it felt when I smacked it into the other one.
Of course, we're not content just to use regular control devices for these grapples. So we decided one afternoon we should control them with a Wiimote.
Alright, just on the camera, you work on a robotic system, the graphical control system.
There's Pygame. Beautiful.
Hey Dan, stand to the left. Yeah. Want to see what you're doing? No.
Yeah, and then everyone came out from the office to have a look. We slowed it right down just in case someone dropped the Wiimote.
We used the Python language extensively in the development of the control system for these grapples. 15 tons of steel, Wiimote, Python, lots of fun.
Well, yeah, crazy times. So that's it from me. Has anyone got any questions? No questions? Fantastic. Thank you very much.